Industrial thermal mass flow meters, also known as thermal dispersion or immersible thermal mass flow meters, comprise a family of instruments for precision measurement of total mass flow rate of a fluid, primarily gases, flowing through closed conduits such as pipes and ducts. The basic physics of thermodispersion mass flow meters is attributed to Louis Vaisseau-King, who in 1914 published his famous King's Law, mathematically describing heat transfer in flows using a heated wire immersed in a fluid flow to measure the mass velocity at a point in the flow. King called his instrument a hot wire anemometer. However, it wasn't until the 1960s and 70s that innovators like Dr. John George Olin, founder of Sierra Instruments, saw the rapidly growing need in industry for very accurate direct gas mass flow measurement. Dr. Olin pioneered the commercialization of thermal mass flow technology, now widely used in a broad range of industrial process control applications spread across global industries. Applications are as diverse as clean energy, natural gas distribution, flare gas, compressed air in manufacturing facilities, semiconductor manufacturing, wastewater aeration, natural gas to burners and boilers, carbon dioxide for chilling food and fermenting beverages, nitrogen and oxygen in production plants, argon for making iron and steel, and the list goes on and on. Standard accuracy is 1% of full-scale flow, but recent innovation, as with Sierra's Quadratherm thermometer, has pushed accuracy to 0.5% of reading, rivaling that of Coriolis meters. Thermal flow meters are often much more economical than other mass flow meters, and have become extremely popular due to high turndown, up to 1,000 to 1, giving the ability to measure very low flows up to very high flows with the same instrument. Since they are rugged and reliable, have no moving parts, are easy to insert via hot tap, have negligible pressure drop, and offer an economical solution to large diameter pipes and ducts, thermal technology has been rapidly adopted over the last decade. So, how does this amazing technology work? In this cutaway view of a typical pipe, the sensor probe is inserted into the center line of the flow. Thermal flow meters have two sensors immersed into the flow stream. One is a temperature sensor, which measures the actual gas temperature inside the pipe as a reference, regardless of the flow velocity. The other is a heated sensor, called the velocity sensor, illustrated here in red. As the name implies, thermal dispersion mass flow meters use heat to measure flow. The velocity sensor is heated continuously via electrical wattage so that a predefined temperature differential is always maintained between the two sensors. For example, 50 degrees Celsius is the constant temperature differential for Sierra meters. As soon as the fluid flow begins, heat is drawn from the heated velocity sensor via the gas molecules flowing past. The heat is dispersed as it is carried off by the flow. To really visualize what is going on, from a molecule's perspective, let's slow everything down and zoom in. Each gas molecule flowing past the heated velocity sensor has an important job to do. As the gas molecule flows past the sensor, it heats up and carries this heat away with it downstream. The corresponding cooling effect is measured and compensated for instantaneously by the instrument's sensor drive electronics, which instantly add more heating current to the sensor to maintain that constant temperature differential of 50 degrees Celsius. This animation shows that the heat is transferred by the actual gas molecules themselves. In a real-world flow application, all of this happens in a millisecond continuously and never stops. In essence, a thermal flow meter is counting molecules that flow past, heat up, then take this packet of heat away with them and carry it downstream. As a result, extremely sensitive, accurate, and repeatable molecular mass flow measurement occurs. So, now that we know the basic measurement principle, how is total mass flow rate of gas flowing through the pipe actually calculated? The meter's basic output is the electrical wattage carried away by the molecular flow. As the mass flow rate increases, the wattage increases. As described by King's law, it turns out that the heating current required to maintain the constant temperature differential between the two sensors is proportional to the cooling effect caused by the gas molecules flowing by, and therefore is a direct measurement of total gas mass flow rate in the pipe. Now let's take another look at a cutaway view of a pipe with gas flowing through it. We have animated the molecular heat dispersion or cooling effect across the sensor that is occurring. You can see from the meter display on the right, the gas flow is 33.0 standard cubic feet per minute. The yellow dotted line represents the heating current sent to the sensor by the meter electronics. Now, let's increase the gas mass flow velocity 10 times to 330 standard cubic feet per minute. You can see much more heat dispersion. The meter immediately reads a higher flow rate, and much more electrical power is sent to the velocity sensor to maintain the constant temperature differential required. It is important to note that heat transfer from flowing gas is affected by the properties of the gas. These are known gas properties like thermal conductivity, density and viscosity, and heat capacity. All of these must be understood and accounted for when a thermometer is calibrated to assure best accuracy. For example, at the same mass flow rate, a hydrogen molecule will carry away more heat because it has higher thermal conductivity than, for instance, a nitrogen molecule. The thermometer must account for this difference to be accurate. So, with this in mind, what is the purpose of a flow meter? This is an important question to think about. The purpose of a flow meter is to transfer an accurate calibration to the field. As a result, a flow meter is only as good as its calibration. Thermal mass flow meter manufacturers must assure that the instrument is calibrated on a closed-loop gas calibration system that is traceable to a national standards laboratory, such as NIST for the United States. Sierra Instruments uses a state-of-the-art NIST traceable closed-loop gas calibration system that is charged with the actual gas to be measured and set to the actual temperature and pressure of the end-user application. This perfectly simulates the customer application environment for a quality calibration, assuring the highest possible performance in the field. Be careful of blow-down or open-loop calibrations, as they operate at ambient conditions and are only done on air. As a result, any other application environment will be inferred indirectly, introducing uncertainty, and thus produce a less accurate meter. Be cautious before purchase. It is highly advised to check with your thermometer manufacturer if they calibrate on a NIST traceable closed-loop system. For accurate and repeatable gas mass flow measurement, down to the last molecule, choose thermal mass flow technology. Experience our passion for flow. For more information, go to www.sierrainstruments.com, the global leader in flow instruments.